In this section, we're going to take a look at some classical problems in process synchronization. So we're going to take a look at the bounded buffer problem again, the reader-writer problem, and then the dining and philosophers problem, which maybe you've heard of that last one. So basically what these are going to be some sort of, one thing is they're canonical examples, right, of how threads might interact, right? These are going to be problems that, oh yeah, I can imagine, software needing to address, right? Then from that kind of problem description for each of these, we're going to take a look at some implementation that uses semaphores. Now for the last one, we'll talk about dining and philosophers. That implementation will be a little bit iffy. As it turns out, when you have multiple processes running the system, right, one of them may be waiting for one of the other ones, sometimes bad things happen. Specifically, something called a deadlock can occur where basically I have multiple threads, multiple processes running at the same time, and for whatever reason, it's impossible for them to move forward, right? They're in a stalemate, right? They're in a deadlock. And actually later on in this course, we'll actually have an entire section, right, about deadlocks, about how to detect them, how to prevent them, how to design code to make sure they never occur, and that type of thing. So let's get on with our examples. So the first thing I want to talk about is the bounded buffer problem. You may remember this one from a little while ago, right? This is one of our our sample things where we said, okay, I have these two threads working at the same time, right? And they're going to go into this one array of size n, and one of them is going to put elements into it, and one is going to take elements out of it. And then from the source code in the book, we had this idea of there was a circular array going on, right? Where you basically add to one side, take from the other side, right? And then those two different threads, right, would have to wait around if they can't do what they want to do, right? The producer has to wait until there's space available, consumer has to wait until there's an element available. And there's some issues though, right? Because those are somehow competing, right, for access to the same array. They're competing to the access to these these same variables. Maybe things can go wrong, right? So instead what we have here is a solution to that problem where we can be pretty certain nothing's going to go wrong. And the way we're going to get there is by using semaphores. So let's first take a look at the different variables that are going to be involved in this. So I have four things listed here, right? I have n, I have three different semaphores, right? So those different semaphores there, right, those all basically are different ways to control how data is being allowed to change or not change. Okay, so first thing I guess I should say is n, right? So n is going to be the size of our buffer, right? So we said, okay, I have processes going and consuming stuff, also processes going and producing stuff, right? And we had the analogy, right? Maybe it's something like a web server, right? Something is creating requests for pages, something else is actually producing those pages and serving them out, right? Or maybe there's some other computation happening. Plenty of things can kind of match along with this problem. So n anyways is going to be the size of our buffer, right? The amount of work to be done, right? Stuff that's been generated by the producer but hasn't been consumed yet. So n is the number of our total buffer size, right? And we said it's going to be a constant size buffer. Then I have my three semaphores there, right? So my first semaphore, buffer mutex, right? Basically what that's doing is that's my lock to make sure that, oh, only one person is changing the buffer at a time, right? The buffer, we're not really specifying it here. You can just think of it as being something like a list, right, or an array, right? It doesn't really matter. What matters is that the semaphore, right, which we are going to initialize to 1, is the thing that I need to acquire, right? I need to wait on. If I want to make changes to that particular data structure, right? So I'm going to have that semaphore, right? Somebody wants to produce something, they have to wait on that, right? Get a hold of that resource, then they can add something to the buffer, and then they'll signal that semaphore, right, to release it back to the outside world so somebody else can use it, right? But we'll have that semaphore basically to guard access to changing that buffer data structure that we're going to have. And then what I have, right, is two other semaphores, one which is basically called full and one which is called empty, right? So the empty one I'm going to initialize it to n, full is going to be initialized to 0. Basically what that's doing is it's a count of how many spaces I have available. So when I say empty equal n, what that is meaning is that in my buffer of size n, initially I have n empty positions. And then on the other side, right, I have full is set to 0. That means that full has, that array has 0 full spaces, right? At the beginning of time, no one's built anything. The entire array is just empty, right? And so what's going to happen is, as I produce things, right, I'm going to basically lower the value of that empty variable, right? Semaphore, the idea is that a semaphore can count the number of available resources. Here what it's basically counting up is how many empty slots I have, right? That's my resource I'm trying to control. So as I produce things, I will reduce that number, right? Empty will go down, and instead full will go up, right? That resource we're getting a hold of a full, data entry to deal with, right? So that goes up, and then later, right, that'll be consumed by the consumer, right? So anyways, empty plus full in the end will always be equal to n, right? Because for all my slots, either they're empty or they're full, right? I can't have something in both states. It'll have to be in one of those. All right, so let's look over on the right-hand side. Let's take a look at the actual code. So first of all, we have stuff for producer, right? So this is my producer code up top. So I have a loop here. It's just an infinite loop just for sake of demonstration. First thing I do is I wait on empty, right? So empty is a semaphore. It's basically counting the number of empty space resources I have available, right? So it should make sense to wait on that because I need to wait for an empty space to be available, right? I have no hope of producing something and be able to store it unless there's empty space. So I'll have to wait on that. So let's suppose, right, that is a positive value. Therefore, that wait, right, I want it to sit there for a while, right? It'll just go ahead and grab that resource. It'll reduce that number for empty down by 1, right? You're doing a wait, so you're subtracting that 1. All right, so I know that I have an empty space to produce stuff into. Well, in that case, I want to go and try and do a wait on the semaphore for the buffer, right? That mutex, right? Basically, even though we're saying it's a semaphore, right? We're initializing it to 1. It's just acting like a mutex, right? It's acting like this variable that controls it so that only one particular part of the program can have access to a resource at a time, right? Either you have that lock or you don't have that lock, right? Either it's a 0 or 1. So we wait around there, right, for our producer, right, to get a lock on that buffer, right? Once we have a lock on that buffer, then we can actually go and take whatever it is we're producing, right, and put it in an empty slot, right? We know there's going to be an empty slot because, well, we had that initial wait, right, on that empty semaphore, right? So we know there's going to be space. We have unique access to it, so we're free to put stuff in. All right, done putting stuff in. At that point, right, we're going to signal on the mutex, on the buffer mutex, right? So basically, we're saying, okay, I'm done using this thing. Somebody else can now have access to that array buffer to add or remove stuff into. So that's fine. But then at the end, right, we have a signal on full, right? So in the past, right, we've seen things like, okay, whenever I do, a wait on this semaphore or this mutex, well, then later on I'll do a signal on that same mutex or semaphore, right? They're kind of matched up. In this case, it's going to be different. The reason it's different is because we're consuming full resources to create, we're consuming empty resources, right, to create full resources, right? So we did our wait on empty, right, to reduce the number of that. But then when we're done, at the end of the day, a slot has been populated with data. And so really we want to do our signal on that full semaphore, right, to say, okay, there's one more of this resource type available, right? We're kind of moving between resource types, between things that are empty and things that are full, right? Those are both resources, right? It may not make quite sense, right, to say it's something empty is a resource, but really it is. And we're flowing, right? We're moving from empty to full. All right, so that's the reason why the things don't match up. When we talk about the other process, right, other things will go in the other direction, right? We'll basically be decrementing full and incrementing empty, right? All right, so let's take a look at the next part here. So down here, right, we have the consumer. For the consumer, right, we have, again, our wait at the top, right? We wait on full, right? I can't really consume anything, right, unless there is at least, one full, element or, resource, right, in my array, right? I need something to work with, right, to consume. So I'm going to wait there, right? So let's suppose that there is something there, right? It's a positive number. Well, then this wait will go through, right? And then I'll go to the rest of the code of this function. Well, then I have kind of the same code as I had before, where I say, okay, I want to get a lock on the buffer itself, right? Then I can go to that particular index, right, that has something for me to consume, deal with it, right, and then release the lock back, right, so that somebody else can then have a chance to change that array. And at the end, right, I have my signal on empty, right? So all of a sudden I'm showing, okay, hey, even though I did a wait on full, I consumed it, right? And then I basically go and say, okay, I've generated a new empty slot, so I have to do signal on empty in order to increase that again. So that's going to be our basic system, right? We have two different threads, right? First step for both of them basically is to wait for something that they can act on, right? Whether it's an empty space or it's a full space. Then they ask for kind of exclusive access to the array, update it, and then signal to the semaphores what resource should be increased at the end of the day. All right, so our second example is going to be for the reader-writer problem. The reader-writer problem, we haven't seen this before. It's kind of a new idea, but it's something that maybe will make sense. The idea is this. Imagine you have maybe a file on a disk somewhere, right? And it's just out there, right? Well, parts of your system may want to read from that file. They may want to write from that file. How do we set up your system so there is no kind of no race conditions, right? Nothing goes wrong. The data doesn't get corrupted, right? How do we make sure that that set of readers and writers are going to kind of collaborate in a way that will produce kind of a correct data file at the end of the day, right? That's what we're doing. So we have basically a class of programs that are going to be doing writes, a class of programs that are going to be doing reads, right? And then we have the source code for both of those, right? And our goal is to say, okay, if I am a writer, well, then only one writer should be allowed to write the data at any particular time, right? Otherwise, if I have two people trying to write, well, then who knows what's going to be my result at the end of the day, right? It doesn't make any sense. I'm not sure what it'll be. Also, right, I don't want to write and read at the same time, right? Because what happens if I maybe read through part of the file, then I write to it, and then I do another read, right? Maybe I'll get duplicate data. Maybe I'll get some sort of garbage data, right? Again, that's something I want to prohibit. So if so basically what I'm saying is one person should be allowed to write, and nobody else can write with them. Nobody else can read with it at the same time that they're writing, right? For readers, I'm a little bit less restricted. For a reader, I can say, okay, hey, if someone's reading a file, well, then somebody else can read it as well, right? I can have any number of readers, right? It's not a destructive operation. It's not going to change the state of that file. So it's fair game for me to have several different threads all reading at the same time. So that's kind of the situation I have, right? So just think to yourself, many programs reading, many programs writing, one file on disk. How do we handle that? So what I have are 3 variables, right? You can look at this at the bottom left-hand side. So I have 2 semaphores and an int. So the first semaphore, rw_mutex, is basically saying, okay, is anybody messing with this file, right? So whether it's a reader or a writer, who has kind of access to this thing right now, right? Because I want to make sure that nobody else can manipulate this resource while somebody's writing to it, right? There's the same idea, right, as having that buffer mutex on the previous example, right? We just want to have some sort of way to lock access to this particular resource, right? This particular file that we're interacting with, and making sure that only one person can use it. So that's going to be our first variable there, rw_mutex. Next we have rc_mutex. And rc there is actually standing for the reader count at the bottom, that other variable. These two things actually kind of go together. The reader count variable is basically a variable to keep track of the number of people who are reading from a file. This is going to be useful for us later because, well, we'll see why it's useful. But maybe the point there is, oh, it's fine to have multiple people read in parallel. We don't have a variable for the number of writers because that would be unsafe, right? Only one person should be allowed to write at a time. It's reading that's the operation that's safe for us to do. Have multiple people doing it at the same time, right? That's fine. The rc_mutex is basically a mutex to protect access to the reader count variable, right? So whenever somebody goes and maybe they want to say, oh, I'm an extra reader, so I'm going to increase this, or maybe I'm done reading, so I'm going to decrease it, right? Whatever thread wants to do that has to go through that read count variable mutex, right? rc_mutex variable, right? So only one of them can change that at a time. All right, so let's take a look at the programs. The program on top that I just highlighted is for the writer. So basically the writer is, well, it's relatively simple. Basically it says the following, right? So the writer wants to write data. Well, that means he needs to wait on the rw_mutex, right? We said there was going to be this one mutex, which basically is the protection for who gets to mess with this file, right? Who gets to write to it, who gets to read from it. So the writer has to wait, right, until it acquires that mutex, right? And if they have to wait around, right, maybe it's because somebody else is writing from it, maybe because it's somebody else that's reading from it, right? As far as those operations, we want to make sure that file is being, basically whoever is interacting with that file has kind of exclusive access to it, right? We don't want multiple people to be messing with this thing at the same time, at least for writing. So wait around, right, until you're the only person, that's looking at the file. You're the only person that's writing. You're the only person that's, well, you're not even reading, right? You're just doing your stuff, right? Nobody else is reading. Nobody else is writing. All right, so grab that lock. Do whatever you want, right? So maybe you add some stuff to the file. Maybe you move some stuff to that file. You can do whatever you want. And then you do a signal, right? So you release that mutex back to the system. All right, so fine, right? We have basically a resource being protected by a mutex. We've seen this before. Now, what's more complicated is the bottom part here, which is the reader process. So the reader process is actually pretty long, and we'll see why in a second. So the first part there, right, wait rc_mutex. So basically, when a reader wants to go, the first thing it actually does is waits on the read count variable because it wants to update, right? That variable is supposed to count the number of threads that are waiting for, well, it's supposed to count the number of threads that are currently reading from that particular resource. So wait on that variable because we want to make a change to it. Let's say we get it, goes in the next line. Read count plus plus, right? So one more person is reading. Now the next line is kind of interesting. If read count equal 1, wait on rw_mutex. So let me put it this way. The first reader on a file is charged with acquiring the RW lock, right? So somebody else could be, writing to the file at that time, right? So we're trying to acquire that lock because we want to be the only person that's messing with that file, right? We don't want to be competing with anybody else. But rather than having every single reader wait on that RW variable, only that first one, right? Only if you happen to be the first reader do you make that happen, right? So first reader through grabs a lock on the file. And then, right, we kind of continue on. We release the lock on rc_mutex, right? So somebody else can go and increase that variable. So now that I have my reader and I have, right, I've increased read count by 1, I now have that RW lock in place, or rw_mutex in place. So I can go and do my stuff, right? I can read whatever I want. So then after I'm done with that, right, I do another wait on rc count, right? Because I want to get access to that variable again so I can decrement it. All right. So there's also the if statement in there again, right? And the if statement looks a little bit interesting. Basically what we say is, hey, is read count equal to 0, right? So basically, are you the last one out, right? The reader that this code is running in, are they the last one to actually be doing stuff? Well, if they are, then it'll be their responsibility to release that RW lock, right? So somebody else in the system, whether it's a reader or a writer, well, it's not going to be a reader. Maybe think about that yourself. But it could be a writer, right? Some other writer can go and use that resource. All right, and so then once we've done that, last thing in there, right, is to say, okay, I've decremented my read count already, so then I can release that RC mutex as well, right? I'm done updating that file. All right, so here's maybe the overall picture. Imagine you are a reader. First reader to open a file is in charge of acquiring the global lock that says, I'm the only person to change this. If another reader comes along, though, and sees that, oh, hey, somebody is already reading this file, they do not have to worry about acquiring that lock, right? One person is already reading from it, and they're already making it safe for themselves by acquiring that lock. Second person through, third person through, fourth person through, right? None of those have to worry about acquiring that same lock. As long as that lock is held by the first reader, then anybody else can kind of piggyback on top of that and read the file as well, because we know it's not going to be changing. Later on, right, they can leave, and as long as they're not the last one, they don't have to worry about anything, because, oh, well, that lock needs to stay in place so that everybody who's reading, they don't get into trouble. Until you get to the very end and that last person out, right, that last thread out, then they'll need to release that lock on the main file so that somebody else can go and write to it in the future or maybe read to it in the future. All right, so that's the general idea, right, which you have only the first thread of the readers is responsible for reading and locking the main resource. All right, so the last thing I want to talk about in this section is the Dynamic philosophers, which is a kind of a very, very, very classic problem in concurrency in terms of computer science. There I have my image on the side, right, I have my famous philosophers. This is, borrowed from Wikipedia. I have the citation somewhere, I just didn't make it into the slide. I had big plans at first. I was like, okay, maybe I should go and replace each of the philosophers with one of the faculty members here, but I didn't have time and I'm not that good with Photoshop, so I'll leave that for another day. Anyways, what we're going to be talking about is this general problem. So the problem is as follows. Imagine you have a table, 5 philosophers potentially hungry. If they're not hungry, then maybe they just want to talk with one another about philosophical stuff, right? So they could be talking, they could be eating, or maybe they're just hungry, right? Each of these people have different things they're currently doing. So we have 5 philosophers sitting on the table. Let's say in front of each of them we have a plate of food. Okay, fine. But then to each philosopher's side, maybe you have something like a utensil, or maybe they all have, let's say the easiest thing is to imagine they have essentially chopsticks on either side of their bowl. So I have 5 philosophers, 5 chopsticks on the table. Okay, this is what's going to happen. I'm going to say, at some given time, our philosopher's going to get hungry. They're going to reach to either side. They're going to grab the chopsticks. They're going to eat. Okay, fine. And then they can go back to talking about stuff. Somebody else does the same thing. Fine. Well, the problem is that there is basically a state the system can get into where nobody is going to be allowed to eat. Right? Maybe think to yourself, oh, how could that happen? Right? Is there any way a philosopher could essentially starve to death? Take 1 second to think about that. Well, so maybe what occurs to you is the following. 5 philosophers at the table. They all get hungry at the same time. They all reach to the right-hand side and pick up a chopstick. They look to the right-hand side. There's no chopstick there for them to pick up, right? They need a set. They need 2 of these resources, right? There's chopsticks are the resources in this case. So I would go back to talking in terms of SE stuff. I need to acquire 2 chopsticks, but everybody's holding one. I can't get another one, right? So all of a sudden there's a stalemate, right? All these philosophers can't continue, right? What needs to happen, right, is somebody needs to put down a chopstick so that somebody else can pick it up and they can eat, right? If nobody's willing to put down a chopstick, well, then basically they're all going to starve to death, right? None of them can actually acquire both resources, right, both chopsticks that they need in order to advance, right, in order to go to that plate and pick up food and eat for themselves, right? It's simply impossible, right? So this is the problem of the Dynamic philosophers. I don't have enough resources to ensure that all my actors, right, all my philosophers, all my processes can move forward their computation, right? Because the processes or the threads have to acquire certain resources before they can do stuff. If everybody gets kind of stuck partway through acquiring the resources and can't ever get the rest of it, they're never going to be able to proceed. It's what we call a deadlock. So we do have a kind of a solution here, right? Maybe you can look at it and kind of see where it goes wrong, right? So this is what would happen if we tried just to implement this basically with mutexes / semaphores. So we could have, right, this loop for a philosopher who's trying to eat, and they basically say, oh, I'm going to wait on the chopstick that's to my right, wait on the chopstick that's to my left, right, either side, basically at position I or I+1. The mod M thing is basically saying, oh, it's a round table, so the philosopher at the end can wrap around and grab, the chopstick on the other side, right? It's just a circle. There is no end. So normally this code is saying, hey, you're going to go and acquire both these resources, do your stuff, and then release both of those resources. But again, we have the issue of, okay, hey, everybody grabs one chopstick. That's equivalent of everybody basically doing one wait. And then when they go to acquire their second resource, right, they go to do that second wait. Well, there's nothing there, right? And nobody's going to put a chopstick back down, right? Nobody's going to release a resource because they're just, they have half what they need. They don't have all of what they need, right? So they all just get stuck together. So this code right here, this code is problematic, and there's a chance that a philosopher might starve to death.